Hello and welcome to this video on series RLC circuits. In previous videos we've encountered these three components separately, namely resistors, inductors and capacitors, and in this video we're going to look at what happens when these three components are placed together in series with an AC supply, so hence series RLC. First of all, let's define some component parameters. We have a supply voltage at the bottom here. Let's say that supply voltage Vs is equal to 120 volts at 50 hertz. So it has a frequency of 50 hertz there. Let's also say that the resistor in this question, R, is a 100 ohm resistor. Let's say the inductor, L, has an inductance of 560 millihenries. And finally our capacitor, C, let's say that that has a capacitance of 20 microfarads. So in this video we're going to first of all calculate some reactances of components and the impedance of the whole circuit. And we're also going to calculate currents and voltages within the circuit. It is worth mentioning that in this example we're going to look at some of our calculations and answers in polar form or in complex numbers. If you're not so sure about complex numbers, it's worth going back and checking out the videos on that topic. But let's first of all begin by defining the reactance in this circuit. We have three components here: resistance, capacitance and inductance in the circuit. And we know that capacitors and inductors have the property of reactance when they're in an AC circuit. So let's begin first of all by calculating the reactance of our inductor L, and we'll call that XL, the reactance of the inductor. And we know that the formula to calculate the reactance of an inductor is 2 pi FL. 2 pi times the frequency times the inductance. So substituting some values in here, 2 pi times the frequency, which is 50 hertz, times by L, the inductance, which we said is 560 millihenries. So that's 560 times 10 to the minus 3. And calculating that gives me an answer of 175.93 ohms. Let's do something similar for the reactance of the capacitor, the other reactance in our circuit, XC. And the formula for the reactance of a capacitor is 1 over 2 pi FC. And likewise, we can put some values in here. We can say that that is 1 over 2 pi times 50, the frequency, times C, which is our capacitance, which in our case is 20 microfarads, 20 times 10 to the minus 6. And that comes out with an answer of 159.15 ohms. The next step in this particular circuit is to calculate the impedance of the whole circuit. And the impedance is really the combination of both resistance and reactance in the circuit. Now the temptation is to say, well, because resistance is measured in ohms and the reactances that we've both calculated are both measured in ohms, the impedance is simply just a case of adding all three of these parameters together. Now, unfortunately, it's not quite as simple as that, and I'll try and illustrate with a sketch. We're going to try and represent our resistance and our reactance as a complex number. And to do that, we need two sets of axes. So resistance is going to be a horizontal axis going along the bottom here, and reactance is going to be a vertical axis going up the side. And this is because we're representing resistance as a real number going along our sort of x-axis, as it were, and reactance is what's called an imaginary number, going up the y-axis, and together we're going to use those to calculate our impedance. Now we have two reactances in this circuit. We have the reactance of the inductor and the reactance of the capacitor, and as such we have to represent both on our diagram. And the way we do that is actually by representing the reactance of the inductor, the inductive reactance, as a positive number going up, and the capacitive reactance as a negative number going down, but they're both on the sort of y-axis, the imaginary scale in our complex number. Again, if you're not sure about complex numbers, it's probably worth revisiting the topic before tackling the rest of this question. But let's plough on ahead and try and sketch this diagram. First of all, we have our resistance, which is going along here, and R is, in our case, 100 ohms. So I'll put that on my diagram as well. We've also calculated our inductive reactance, which was 175.93 ohms. So I'll pen that on here. XL is 175.93 ohms. But we also have our capacitive reactance, and our capacitive reactance should always be in the downward direction, and that comes to a value of 159.15 ohms. That's what we calculated on the previous slide there, and that was XC. Now, to simplify the process here, you'll see that we have our inductive reactance pointing in this upward direction, and we have our capacitive reactance pointing in this downward direction. They oppose one another. And so what we can do is we can actually cancel these two down to simplify our diagram. If we have 175.93 going up and we have 159.15 going down, then we can simply calculate the difference between them. And the difference in this case works out to be 16.78. So 175.93 minus 159.15. So we can simplify our diagram a little bit by doing away with both of these. So I'll take those out there and replacing it with just one simplified version, as it were, which is going to look like this. It's going to be just whatever the difference between them was, 16.78 ohms, and I'm going to call that XT, the total reactance. So that's taking into account both the inductive reactance going up and the capacitive reactance going down. So now that we've calculated the total reactance in our circuit, and we're also aware of the resistance in our circuit, we can use both of these to calculate our impedance. And the best way to do this is to visualize our impedance triangle. So if we have our resistance going off to the side and our reactance going up the side there, then the resultant of these two is going to be our impedance. And I'll try and draw that on like so. So our impedance, if you can imagine, being the sort of completing the hypotenuse of this triangle that we have here, where the side, the vertical side, is 16.78 and the horizontal side is 100. So to calculate the length of our sort of diagonal, our hypotenuse there, is actually going to give us the impedance of our circuit. And as a result, we can use Pythagoras' theorem. We can say that Z squared, the hypotenuse as it were, is equal to R squared plus XT, the total reactance squared. And so substituting some values in here, R is 100 ohms, so 100 squared, plus our total reactance squared, we said was 16.78 squared. And calculating that gives me a very large number, 10,281.57. I'm not too interested in that number because I'm not calculating z squared, I'm just calculating z. And so I want to find the square root of that number. Z squared is 10,281.57, but z is only going to be the square root of that, which is 101.40 ohms. We can also calculate the angle in our impedance triangle, and I'll mark that on my diagram here. Our angle is going to be this angle here, and calculating that angle is going to help us calculate the phase angle of different currents and voltages that we want to calculate later on. So we can do that very easily using trigonometry as well. If we know our trigonometric identities, we can say that here's our hypotenuse and here's our marked angle. So this side of the triangle, as it were, which is the same length as this side here is the opposite of the triangle, and this side is the adjacent of the triangle. And so one of the best identities to use in this case would be the tan identity, tan of the angle being equal to the opposite divided by the adjacent. We're going to rearrange that very slightly. We're going to say that the angle itself is equal to tan to the minus 1, opposite over adjacent, and in our case the opposite is 16.78, and the adjacent is our resistance 100. And if I calculate that, I get an angle of 9.53 degrees. So now that we've calculated the impedance of our circuit, we can go ahead and calculate the current that flows through our circuit. We have a series circuit, so there's only one current. The same current flows through all three of our components, and we can calculate that by using Ohm's law. So we're simply going to say that the current I is equal to V over Z, the voltage divided by the impedance. So in this case, we're going to continue to use polar form in our calculation. So the voltage is 120 volts, but we're going to say that that's 120 volts at an angle of 0 degrees. In this case, our supply voltage is our reference phasor, and so that's going to be at 0 degrees. And we know from our previous slide that the impedance comes out at a value of 101.4 at an angle of 9.53 degrees. And so when we're dividing in polar form, we divide the actual first term, the number of the answer, and we subtract the angles. So we'll end up with a result of 1.18 at an angle of minus 9.53 degrees. Now that we have the current that flows through the whole circuit, the last thing that we can calculate in this circuit is the voltage across each component. We know the supply voltage, the voltage that's supplied to the whole circuit, but some of that voltage will be dropped across the resistor, some of that voltage across the capacitor, and some of that voltage across the inductor. So what we can do is again use Ohm's law to work out the individual voltages dropped across each component. Let's begin by calculating VR, the voltage across the resistor. And so VR, again using Ohm's law, is going to be current I multiplied by the resistance R. We know the current I from our previous slide. We said that it was 1.18 at an angle of minus 9.53 degrees. And we're multiplying it by the resistance. The resistance we're given in the question, 100 ohms. And again, we're trying to use polar form. Resistances don't have a phase angle. So it's 0 degrees. Multiplying those two terms together, we can say that we have an answer of 1.18 multiplied by 100 at an angle of minus 9.53 plus 0. We multiply the numbers themselves and we add the angles when we're multiplying in polar form. And so we get a result of 118 at an angle of, again, minus 9.53. And that's a voltage, so volts. Let's do exactly the same for the capacitor in our circuit. So VC, the voltage across the capacitor, is again going to be I, the current, multiplied by not the resistance this time, but reactance XC, the reactance of the capacitor. And so we can substitute our values in once again. We can say the current is the same current, 1.18 at an angle of minus 9.53. We can also say that our reactance, which we calculated right back at the start, is 159.15, and remembering that it's a reactance and not a resistance, we have to include a 90-degree phase shift. So capacitors, their reactance is at minus 90 degrees relative to a resistance. So again, multiplying those two terms, we come out with a result of 187.8 at an angle of minus 99.53 degrees. And again, that's a voltage. Lastly, exactly the same method once again. VL is going to be I times XL, and the same thing applies. Our current is 1.18 at an angle of minus 9.53 multiplied by the reactance of our inductor. And just like capacitors, inductors also have a reactance. The reactance also has a 90-degree phase shift, but this time their reactance is at 90 degrees relative to a resistance. Our reactance, if you remember, was 175.93, and that'll be at an angle of 90 degrees this time. So our final calculation is going to give us a result of 207.60 multiplied, at an angle of 80.47 degrees. And again, that's our final voltage. So what we can see here is that we end up with three separate voltages across the three separate components. One thing you might notice is the size of these voltages actually comes to a total far greater than our original supply voltage. And there's a reason for that. It's called voltage magnification, and it's one of the strange effects of our series circuit. The reason being, we also need to take into account the direction of our phasors. And so what we'll find is that 187.8 volts is actually pointing in a fairly downward direction with this negative phase angle, but our 207.6 volts is pointed upwards or tilted upwards with its phase angle being positive. And so these two in total will somewhat cancel out and will leave us with a total of what we originally set out with our supply voltage. But when measured individually, we can actually get some very high voltages. So voltage magnification is one of the unusual features of series RLC circuits. So I hope you found this video useful, first of all on looking at series RLC circuits and being able to calculate the currents and voltages within them. We're going to look at some more examples in later videos of RLC circuits and also the concept of resonance.